I'm very happy to introduce Professor Colin Wilson from the Cognitive Science Department here. Colin actually did his PhD here with Paul Smolensky, I think. No,
Luigi.
With Luigi, sorry. A number of years ago, and then he went off and got tenure at UCLA, which is one of my favorite linguistics departments, and then immediately returned to the nest, where he is honoring us by giving us a practice talk. And knowing this audience, I'm sure that we'll all give him plenty of feedback. I should say he's especially known for his work in experimental phonology, and that includes computational experiments, which we'll see some of today, I think.
It's conceivable if we get there.
Okay.
Yeah. Thanks, Jason. Thanks to all of you. Yeah, you're my guinea pigs for Yale, so feel free to give me hell. I mean that. You can interrupt me whenever you want. We can make it as informal as you like. So I'm going to be talking about a constraint called the OCP-Place, and let me just thank some people who have helped me with this work. So I've been collaborating with Marieke Obdane, who's a graduate student in our department. And Matt Goldrick has been helping me out as he always does. And a lot of people have shared their data with me. They may not be happy with what I've done with it, but they were gracious to give it to me. We know that in all areas of grammar, phonology included, languages vary from one another in ways that we can't always predict. So one that you may have heard of and that's gotten a fair bit of press is this distinction between English and Japanese. English allowing sequences like kta, but Japanese not. Japanese has structures that we don't have in English. Japanese has long consonants like in katto that we don't have in English. So this is just a dimension of variation, and there are all four of the possible types of languages in this little picture. And nothing that I'm going to say today is going to solve this problem of variation. This isn't a problem of variation that one can really solve. So to account for native speakers' knowledge, the fact that English speakers know, for example, that they can have sequences like this, but not of that other type, we need to have some learning theory, some strong learning theory that will allow the infants and other language learners to pick up on the unique properties of their language. The flip side of variation are linguistic universals or laws. So we know that there are limits to the range of variation in language. Certain laws are obeyed by all languages that we know or all languages that have been attested. And many of these observations go back to the work of Roman Jakobson and Joseph Greenberg and others. So for example, if we just look at what consonants are possible between vowels, there are some cases in which we have a lack of variation alongside the cases of variation that we saw before. So for example, every language that allows you to have a sequence of two consonants between a vowel will also allow you to have one of them. So this cell in this table is not the language none. There's no language that goes in that cell, okay? So universal laws indicate biases. They could be hard or strong, as you're familiar with from the machine learning literature, that restrict language learning or maybe language use. And I'm going to be talking about what I think is a linguistic universal or a law, but something which has claimed not to be. So the strategy for finding universals is to not give up when the going gets tough. So given any case of reported variation, someone who's searching out language universals has got some questions to ask. So does the evidence really support the claim that there is variation? Sorry. Can we explain the variation as the result of the interaction between one principle or dimension that we're looking at and other independent principles or constraints or dimensions? And if we do find a case of variation, if we haven't found another universal, strictly speaking, we still want to know what the limits to variation are. So the goal of this kind of universalist approach to language, looking at what's common across languages, is not to deny that in some cases significant learning is going to have to be done, but rather to determine cases in which learning would not, strictly speaking, be necessary. So this talk is about a case that appears to fall between the poles of universalism or universality and variation. And that's the OCP-Place law. So it turns out, and for reasons that I don't think anyone fully understands, many languages disprefer consecutive consonants in a root, in a noun, in a verb, in an adjective that have different instances of the same place of articulation. So there's a nice survey of this that's been done recently that looked at a lot of African languages that hadn't been studied, but if you look at any language family, you will find good instances of this law. Two of the now most well-known cases come from different language families. So Arabic is the case that is most well-known. There are roots like katab, kataba, all three of those consonants having different places of articulation, but no or very few roots like kagab, where ka and ga have the same place of articulation, or something like katad, where ta and da do. I bolded the consonants because I'm not going to have anything to say about vowels today, so if you ever see a vowel in one of these forms, you can just ignore it. I'm only going to be talking about the consonants. Maybe the vowels are important too, but I don't know about that. A more recently studied case, but kind of a celebrated one now, is Muna, which is an Austronesian language. And Muna has roots like kabo and kado. These are actual nouns or verbs of the language. But not a lot of roots like kago, where ka and ga have the same place. So we think that there is an OCP-Place law, but there's still a question of whether there's significant variation in the precise details or precise form of that law across languages. And the first generative phonologist to really address this issue was John McCarthy. And he proposed that, in fact, you need several variants, several versions of the OCP-Place law for different languages and for different parts of a single language. And I'll be arguing against that view to a certain extent. So the proposal is going to be as follows. Yes, Jason?
Do you want to say anything, or will you say something later about the axes of variation?
I will, absolutely, yeah. Okay. Yep. So basically the idea is that you're able to add codicils to an OCP-Place constraint in a particular language that exempts certain consonants from being subject to it. Okay. Because they're not similar enough on some other dimension, some non-place feature.
Okay, so this has to do with which things count as similar. Is there also variation in whether this happens across morphemes or only within morphemes?
There is variation in whether it happens across morphemes. As far as I know, every case that's been studied has shown that it holds in some form within morphemes.
Thanks.
Okay, yeah. Yes?
Yeah, can you go back to the last slide?
I sure can.
In the first bullet point, would you consider aspirated and non-aspirated versions of a consonant to be different tokens of the same token?
There are, in addition, so that raises a couple of issues. In addition to OCP restrictions on place, there are often restrictions on aspiration. A restriction that if two consonants, for example, are otherwise identical, they can't differ in aspiration. We're going to get to the details of what I consider to be identical or highly similar consonants, but yes, they would. Those would count as very similar. So why did you ask?
Yeah, my reason for mentioning that is that you're claiming that maybe all languages would disprefer different tokens with the same. If you consider aspirated and non-aspirated as different tokens, then I can guarantee you there are lots of Indian languages which allow the aspirated and the non-aspirated versions to occur next to each other.
Mm-hmm. So this law.
Sorry, just one more.
Yeah, sure.
Just to make sure everyone understands the phenomenon and that I do as well. Yeah. In your first example, kebab is fine, right?
Yeah. So there's a point of variation.
Identical or substantially different, but they can't be similar.
Yeah, so there's another point of variation, which is whether identical consonants are subject to this restriction, and if so, when they are. And so we won't talk about perfectly identical consonants, and I chose my examples to evade that point that Jason is making, but that definitely is a point of variation, and there are debates about whether those two consonants are really different tokens of the same consonant, or two tokens of the same consonant somehow spread out over time. Okay? Yeah. So just to get back to your point, the OCP-Place law doesn't have to say that similar consonants that share place are impossible. It can say that they're just preferred relative to those that don't share place, all other things being equal. And that's the form I'm going to be arguing for. So maybe it was stated a little bit too strongly. Good questions. Okay. All right, so I'm going to argue that the OCP-Place law can be given a universal definition, but we have to get some other pieces of the puzzle into place first. So we need to know how to define consonant similarity, and I'm going to argue for a particular definition not due to me, due to Stefan Frisch. It doesn't involve counting the number of features that the consonants share, which is probably the most intuitive definition. We're going to have to know how to analyze data of the type that I'm talking about statistically. So we need to, for example, look at the number of times two consonants co-occur and figure out whether there's a constraint on their co-occurrence or not. If they're supposed to be subject to the OCP-Place law, are they in fact subject to it? Do we get fewer of them than you would expect otherwise? So I'll have a particular take on that, and I would like your feedback on this business of O over E or observed over expected, which I'll come to later, particularly today. I'm sure you all can help me out with that. I'm going to give a bit of short shrift to my analysis just because it's so simple. Once we go through these other parts, you'll see how this analysis works, and it seems to work beautifully so far. So I'm going to talk a little bit about OCP-Place and the types of variants that have been proposed by McCarthy and others. And then we'll go through these other parts that I mentioned. Greenberg, in addition to the medieval Arabic grammarians, brought the OCP-Place effect to our attention. And so he looked at a large list of really classical Arabic nouns and verbs, roots, that he had compiled. And linguists have passed around this list of roots amongst themselves for 40 plus years now. So his idea and what he found was in the first two positions of a root, so for example, the ka and the ta in that example that I showed you before in katab, not only identical, but homorganic consonants are excluded, consonants that share the same place of articulation. So no Semitic language has a verb that begins in ba followed by the consonant ma, both of those being labials. None of these languages have ga followed by ka, both of those being velars, or I'll call them dorsals. And so he took the fact that you couldn't have ba followed by ba in those first two positions to be a special case of the fact that you can't get two consonants in those positions that have the same place. If they're identical, of course, they would have the same place. But he pointed out there's a wrinkle, which is that homorganic, having the same place of articulation, doesn't mean exactly what you would expect it to mean. So it requires some consideration, and that's been the problem that many people have addressed. So just to make sure we're clear on some of the places of articulation and so forth before I go on, there's a general constraint known as the obligatory contour principle, which says you can't have adjacent identical elements. And it was first proposed for tone and then extended to other sounds. We're going to talk about the OCP on the place features. So it says you can't have adjacent identical place features. You can have one place feature like this labial here made with the lips that's in some sense associated to two segments. It's just one instance of labial spread out over time. What you can have are two instances of labial right next to one another. And according to the definition of right next to one another, that's relevant when you're only looking at the consonants, you can't have two labials here either. So you see, if you ignore the vowels, these two labial features are abutting one another. That's disallowed. So I'll be using these terms, labial for sounds made with the lips, that includes pa and fa, and coronal for ta and sa, dorsal for ka and ha. And we won't talk about the pharyngals in Arabic, but they follow this same law. So here's the law that we're talking about. No adjacent homorganic consonants in the root. No adjacent consonants that share one of those place features that I was just talking about. But as I noted before, this notion of homorganic is not so straightforward. And here is the sort of crux of the problem. In Arabic, there's a distinction between the labial place of articulation made with the lips and the coronal place of articulation made with the tip or the blade of the tongue. So as I've been saying all along, you can't combine labials in the first two positions, first two consonant positions, of a noun or a verb or adjective of a root in Arabic. So you don't have ba-fa, you don't have ba-ma. And I mean all these pairs to be symmetric, so you can't have fa-ba or anything like that either. But the coronals behave a little bit differently. You can't have da and ta or ta and da. You can't have na and ra, or ra and na, but you can mix those two sets, the set of coronal obstruents, which include da and ta, and the set of coronal sonorants, which include na and ra and la. Those can be mixed together in the first two positions of a root. So you can have, and you do have, roots that begin with na and da, and you do have roots that have that opposite sequence as well. So you can't say, it doesn't appear that you can say as a blanket statement, you can't have two consonants of the same place of articulation in consecutive positions in a root, because these two have the same place of articulation. They're both coronal, and yet you can find roots that have those. So that's the problem that we'll be referring to over and over, the sort of labial coronal asymmetry in Arabic. Just so you know, the other places of articulation behave like the labials. So it's really coronals that are special for some reason that we're going to try to understand.
Could that be because coronal is just the absence of a place feature?
People have tried to argue that coronal is the absence of a place feature and is therefore exempt from any restrictions that apply to place features. Maybe they get their place features late in some kind of phonological derivation. And that turns out to be very difficult to make work, because there are often OCP-Place constraints on coronals that are highly similar, more similar than na and da are. And so if you make all of the coronals placeless, then it's hard to see that similarity.
What about just those two cases there, DT?
Yeah. So that would be a case that would be difficult to work with. So you could have ba followed by ta, okay, but not da followed by ta. So if da and ta are placeless, there's nothing obvious anyway that's making them more similar in that case than in the case of ba ta. But this is an idea that many people have had. Yeah. Yeah. No, that's okay. You could still probably finagle it. I mean, phonologists are pretty tricky. The other thing is that, so you got to keep your eye on them. The other thing is that we want to use the placeless category for sounds other than coronal in many cases. So it may be that the glottal stop, like in beginning in the middle of is truly placeless phonologically. And so if we use the placeless category in that case, we can't use it also for coronal. So in a nutshell, here's the problem. Pairs such as fa followed by ma and sa followed by na are both, strictly speaking, homorganic. In both cases, the two members of the pair have the same place of articulation. But it's different places of articulation, labial in one case and coronal in the other case. In fact, if you look at the details of these two, the feature differences within these pairs are the same. Maybe if you call S strident, you can get one more feature that distinguishes it from N than the features that distinguish F and M. But that one feature isn't going to buy you a lot. But Arabic bans fa, ma, no occurrences of that, but it allows sa, na. There are about 16 roots that have sa, na, or na, sa at the beginning. So that's the problem. In response to problems such as this one in Arabic, McCarthy and many other people following him have proposed to replace the OCP-Place constraint with several variants on the same theme. So, for example, McCarthy's analysis of Arabic would look like this. There's an OCP-Place constraint on labials and on dorsals, and it just says you can't have homorganic sequences with different tokens of the same place. But the OCP constraint on coronal has a little widget, or what's sometimes called a subsidiary feature, attached to it, which says that two consonants are in violation of this version of the constraint only if they share the specification for sonorant. So da and ta, which are both minus for that subsidiary feature, would violate the constraint if they occurred consecutively in a root. And na and ra, which are both plus for that feature, would also violate. But you can mix sa and na and da and na and so forth. They're exempted by fiat by writing in essentially the exception to the OCP-Place constraint. And so this agrees with the data, and one might imagine that in some simple setting it would be very learnable that there is this special subsidiary feature for OCP-Place coronal, but not for these two in your language. But it doesn't really explain why coronal place is special. So why should it be that the coronals are allowed to combine more freely than the consonants of other places of articulation? So that's what we're going to try to understand. Many people have not really tried to understand that, but instead studied many languages and proposed variants of the OCP-Place that are like the one for Cornell that McCarthy proposed for Arabic. So they include these subsidiary features, these other features on which two consonants must be identical in order for them to violate the OCP-Place. So we won't talk about all these cases today, but we will come back to Muna. So these variants are consistent with the facts in those individual languages. There's no denying it. But they don't follow from any more general principle. They look just like ad hoc exceptions. Okay, so recently, Andries Kotze and Joe Pater have really taken this idea to a limit, to not the limit, but to a limit. And so they've argued that Muna differs from Arabic in the relative strength of features that affect the co-occurrence of homoorganic consonants. And one claim that they've made, for example, is that when two consonants share voice and place, that's a very serious violation of the OCP-Place constraint in Muna, but it would be a less serious violation, they've claimed, in Arabic. And so their proposal is to go pretty far with McCarthy's idea and to have many, many different versions of the OCP-Place constraint. This says this is OCP labial, don't have two labials, but they also have special versions that say don't have two labials that also agree in sonorant. Don't have two labials that are both fricatives or both stops. That's what this stricture thing is. Don't have two labials that are both voiced, and so forth.
So sorry, the three rows here, even though you've labeled them P, T, and K,
Yeah.
correspond to the three, or Cassette and Peter, correspond to the three rows on the McCarthy side.
That's right. So this is,
This is just their notation.
yep, absolutely. This is labial, this is cornal, this is dorsal. Sometimes I'll use capital P, T, and K to refer to those classes, but yeah, that's exactly what's going on. Okay, so we have however many constraints we have here. I think they actually have a few more. But the idea is that all these constraints are independently weighted or ranked or prioritized within a language and across languages. So with these constraints, it's perfectly possible to have the anti-Arabic language in which it's only the cornals that are subject to the strict OCP-Place constraint, but the labials and the dorsals and the pharyngals have that subsidiary feature that refers to that requires them to be identical with respect to sonorant. So there's no reason, given this constraint set, for Arabic to be the way it is. You could have anti-Arabic just as easily. You could have anti-Muna and so forth. Okay, so here's what we've seen so far. Cases such as Arabic disallowing F followed by M, or M followed by F, and allowing cases of S followed by N or the reverse. And difference, so that's a difference between two places of articulation within a language. And differences like Arabic allows N followed by D, but Muna really more strongly disprefers that. They seem to pose a problem, prima facie, for the universalist theory of OCP-Place. All the pairs of consonants that I've talked about so far are strictly speaking homoorganic. They share place of articulation. And therefore, they should all be bad according to OCP-Place. Furthermore, if you were to measure similarity in terms of features that are shared, well, pairs like this are about equally similar. Maybe they are equally similar. Certainly, Arabic na and da share as many features as Muna, na, and da, according to the standard feature sets. So the only solution seems to be to build additional similarity requirements, subsidiary features, into OCP-Place variants on a language particular basis, on a place particular basis within a language. So that's where we are so far. We're going to talk about a different way of defining consonant similarity, which is going to get us out of the Arabic problem, but we're going to run headlong into the Muna problem and have to find a different way out of that. But the universalist doesn't give up easily. So here's the problem from Arabic. Labial pairs like ma, ba, and cornal pairs like na, da are both homoorganic. Arabic allows one but not the other. The members of the two pairs differ by exactly the same features. And you might be thinking, well, maybe ma is just an infrequent sound in Arabic. So the fact that you don't find it paired up with ba or with any other sound could just be an accident. Maybe there aren't many words or roots that contain ma in the first place. That doesn't turn out to be true. These consonants all have pretty similar and high frequencies. When you count them in the following way, just count the number of times, count the number of words, for example, that begin with ma, count the number of words that begin with na. Those counts turn out to be very similar to one another. And it's the same for the other places in the word as well. Okay, so if OCP-Place is sensitive to similarity, we measure similarity by features, then we're going to have to allow these two variants of the OCP-Place. But we're not going to measure similarity by features, and this is where Stefan Frisch comes in. So we're going to talk about natural classes. We assign feature values to segments, and using those feature values, we can pick out classes of segments that tend to show similar phonological behavior, and that's why they're called natural. So given a set of segments, we'll just call it S, each of which has some values for the features in the set F. The values could be just plus or minus. Sometimes people use 0 values as well. Some subset of our set of segments, just call it C or whatever, is going to be a natural class if you can find some subset of the features such that all the members of our set of segments have exactly the same values on that set of features. And the set of features can be empty. So all the consonants, let's say, all the segments in a language would be a natural class. But things get more interesting when we choose non-empty subsets of the features. The key idea that Stefan Frisch had when he was developing his dissertation at Northwestern was that we should measure similarity in terms of shared natural classes and not shared features. And I always thought this was such a crazy idea. But turns out to work pretty beautifully. So here's how it works. Suppose we use these 4 features. What is it, Jason?
No, I just saw why this would work. Okay, go ahead.
Okay, yeah. So here are these 4 features that we can classify the labials. And so let's just say we have ba, fa, and ma. We'll leave out the glide because it behaves, the glide wa, because it does behave specially in Arabic, modern Arabic. So these are the values. And Frisch and his colleagues have represented all the natural classes that you can get out of those segments in this type of lattice structure. So here's the natural class that includes nothing. We can ignore that. Here's the natural class that it just includes ba, because it says, well, you have to be minus continuant, you're a stop. You have to be plus voice. You have to be minus sonorant. You have to be labial. And the only sound that fits that entire bill that has all those feature specifications in Arabic is ba. Similarly for fa and ma, if you drop some of the features, then you get sets containing multiple sounds. Okay, so this is how Stefan Frisch has proposed to define similarity of consonants. For any 2 segments, their similarity is this ratio. It's the size of the set of classes that contain both of those segments over the size of the set of classes that contain one or the other, or possibly both. So for example, the similarity of ma and ba is the same as the similarity of ba and fa, according to this lattice that I gave you. There are 5 classes that include either ba or ma. 2 of them include both of those sounds, if I did it right. Same thing for F. Okay, so don't trust my arithmetic, but that's how it's supposed to work. It's also possible, and may make a connection to other things that you've heard about, it's possible to think of these similarity values as determined by the number of attributes that are shared by the 2 segments. But now we have to think of attributes not as the features, but as membership in a natural class. So this, using some language that may be more familiar, we can identify the set of natural classes defined by feature matrices. And since we're interested in OCP-Place, let's make sure that every feature matrix that we use to define a natural class includes at least one place feature in it. Okay, that's the place sensitivity here. So we take our segment inventory, our buzz, our fuzz, and so forth. We find all the classes that are defined in terms of at least one place feature, along with other features potentially. You can think of us as mapping each segment into a very high-dimensional binary space defined by the characteristic functions of these natural classes. So if we take some segment alpha, we could map it into this space representing it as a vector of 0s and 1s. So you get a 0 here if alpha is not a member of this particular natural class, otherwise you get a 1. You get a 0 here if alpha is not a member of this natural class, and 1 otherwise. And you can just do that given some arbitrary but fixed ordering of the natural classes. So now we've recoded each segment not into its feature values, but into its vector of natural class membership. And then we can define the similarity as essentially a dot product with a particular type of norm in that space. This plus is special because it can't go higher than 1. So 1 plus 1 equals 1, doesn't equal 2. But other than that, there's no problem in defining this as a kind of, a kind of similarity metric in this high-dimensional space. I won't use that, but anyway, you could do it. So here's the first application, and it's to Arabic. And the thing that Jason may have been thinking of, but which I'll reveal to you at this point, is that there are many, many more coronals in Arabic than there are consonants of any other single place of articulation. There are more coronals than there are of all other places of articulation combined. So there are these 15 coronals. All right. So the result is that when we apply this natural classes similarity metric, we get lower similarity for consonant pairs than for matched labial or dorsal pairs. The greater number of coronals somehow expands the space, expands the coronal part of the space, making consonants that would be very similar to one another if they were labials or dorsals less similar to one another because they have all these other members in the same place. So there are relatively few natural classes that can be picked out using labial or dorsal, but there are many more natural classes that can be created with the feature coronal because we're talking about a ratio of shared versus unshared natural classes. All of the things being equal, the more classes we have, the lower that ratio is going to be, the less similar two consonants are going to be. Of course, that won't always be true, but that's in general what's going on. So now we can go back to our OCP-Place constraint and make it sensitive to similarity of this very particular type. And we can say, as essentially Frisch and Janet Beer-Humbert and Michael Brough did, that given two adjacent homoorganic consonants in a root, for example, a root of Arabic, we're not going to say that that sequence is absolutely good or absolutely bad. We're going to say that it's bad in proportion to the similarity of those two consonants that share place. And so that means that all other things being equal, the labial homoorganic sequences like fa and ba are going to receive worse violations according to this constraint than the coronal homoorganic sequences like sa and so forth. So in principle, you can see how this would solve the problem for Arabic. And in fact, Stefan and many others have argued that it solves the problem better than McCarthy's original solution did. Because although you do find sequences like this and not sequences like this, these aren't in some sense as good as you would expect them to be if those two consonants were homoorganic. So their claim is that there's a good quantitative fit between the degree of violation of this constraint and whether it's violated at all, but we're interested in the degrees of violation, between the degree of violation and the actual number of roots that contain a given pair of consonants. So we don't want to really say, as McCarthy's proposal did, that these two are exempt from the OCP-Place. They just violate it less because they're less similar, not because they don't share as many features as this pair, as the consonants in this pair do, but because the other coronals are pulling N and D apart, and there are so few labials that they're not pulling M and B apart in the natural class space. That's a story. Okay, but now here comes the problem. So that seemed to solve all the problems in Arabic. It was by far the best analysis of Arabic OCP-Place that had been given, a great improvement on what had come before. But now Kutse and Pater came along and they said, well, okay, that works for Arabic. And if you were only interested in Arabic, you could say it's universal, but we want to study many languages, see if it works for them. And here's a language it doesn't work for. All right, so Muna is unlike Arabic, as they claimed, in giving greater weight to voice. And I'm just going to leave this as something that we'll work on later. I think we can solve this problem, but we won't focus on this. I'm going to focus on an unexpected similarity between Muna and Arabic. Muna is like Arabic in having a stronger OCP-Place restriction for labial and dorsal consonant pairs than for coronal pairs. We explained that using the natural class similarity metric by relying on the fact that Arabic had so many coronals, but Muna doesn't have that many coronals. It has just about as many labials as it has coronals, and the sets of labials and coronals are very well matched featurally. And so that will lead Coetzee and Pater to reject this proposal that we can have this gradient OCP-Place constraint that's the same across languages as long as it refers to natural class similarity. They'll reject that in favor of that big table of constraints that I showed you before. Okay. So here's the Muna inventory, and you can see there aren't heaps and heaps of coronals as there were in Arabic, and there are more labials, many more labials, twice as many as there were in Arabic. And so the imbalance between the labial and coronal places of articulation is not sufficient here to support the kind of reasoning that we used for Arabic. These sub-inventories are of about the same size, and we'd expect the members to be about equally spaced when they're matched pairs. Now there are fewer dorsals and only one pharyngeal. There's no, we don't have to worry about the pharyngels in Muna. But there are fewer dorsals, and you might be able to use the same type of reasoning that we used for Arabic to account for the restriction on the OCP-Place restriction on dorsals in Muna, but probably not for the labials. So here's where we are. I've proposed to replace the original constraint with one that I've claimed to be universal, though we see problems right now. It's gradient in the sense that it signs numerical violations, not just 0 and 1. And it's sensitive to this type of similarity that I've been talking about. And the good thing about this new version of the constraint, and this is due to Frisch and colleagues, is that it explains the fact that labial, and dorsal pairs are worse than coronal pairs in Arabic. It explains it by reference to something independent about the language, that there are so many more coronals. But we've raised a new problem. How can this OCP-Place constraint operate similarly in Muna and Arabic, being violated more seriously for the labials and the dorsals, given that the inventories in the two languages are not very similar to one another? So that's the problem. Okay, so we could give up now, but we'll just keep plowing ahead. So this is the third part, and this is the part that's more statistical. Maybe you have some things to say about this. So I'm going to argue that a particular statistic that people have used to measure the strength of OCP-Place, in fact, it's essentially the statistic that everyone has used to measure the strength of OCP-Place for a given pair of consonants, is wrong. It doesn't measure what it's purported to measure. And that's not just true for its use in measuring the OCP-Place strength, but it would be true when you use it to measure any phonotactic uncombinations. Okay? So many people from diverse lines of research want to know about the strength of phonotactics like the OCP-Place. So linguists doing what I'm doing, psycholinguists who are studying word perception and production, even sentence comprehension, computational linguists trying to build parsers. They would like to know about the phonotactics and maybe the relative strengths of the phonotactics of a language. All previous studies of OCP-Place and many other studies of other phonotactics have used this statistic called O/E. And one might ask, but in fact no one has ever asked, whether this is a valid method or not. Okay, well anyway. So it was proposed by Janet Pierre-Humbert in a paper on Arabic OCP-Place in 1994. And so here it goes. If you give me two finite sets, you can think of them both as sets of consonants. And we'll just refer to remembers of these sets in a kind of kludgy way by putting these indices in parentheses afterwards. If you give me these sets and you give me a corpus or a data set of pairs that are drawn from the Cartesian product of those sets, and let's suppose the total size of my corpus is n. My corpus is just a list of these pairs. The over-E value for a given combination, one member drawn from the set A, another member drawn from the set B, is defined either in this kind of complicated way or in this simpler way over here. It's the proportion of the data set that has AI followed by BJ, which is written in this way, that has the pair AI, BJ. So that's the proportion of the data set that has that, divided by the product of the proportion of the data set in which the first member of the pair is AI, times the proportion of the data set in which the second member of the pair is bj. Okay, so big O is just the frequency of this pair in your data set, frequency of two consonants, for example, in the roots of Arabic. This observed frequency you just get by summing over all the possibilities that could occur in the second position, and similarly for the definition of big O, subscript bj, and so forth. And then to get these proportions, you just divide by the total sample size, not complicated. Okay, so you might think to yourself now, why are we bothering to divide by anything? Why don't we just take the raw frequency of co-occurrence of these two sounds, or the proportion, just divide by the total size of our corpus? Why don't we take that as our index of the strength of the OCP-Place or other phonotactic against them? Why are we also dividing by these other terms? And why are these two multiplied by one another? Okay, so in the general case, this set would be the set of consonants that can occur as the first member of a pair in a root, or maybe a set of consonants in general. And B would be the set of consonants that can occur as a second member, and we would calculate O over E for every pair. And for a given pair, if they're homoorganic, we would take the O over E value to be an index of the strength of the OCP-Place constraint against them. The lower the O over E value, the thinking goes, the stronger the OCP-Place should be. Let's do something simpler. So let's just imagine we had three consonants, big P, big T, and big K. And they could occur in the first position or the second position of one of these nouns, verbs, or adjectives, one of these roots. And suppose someone handed us this data set where they've cross-tabulated the first and second consonants. So I'll show you where this data set came from in a second, but it's a fabricated data set. So they showed us, well, there are 249 cases in which big P was followed by big P. Abstractly speaking, right? Some labial followed by some labial. And there were more instances in which T was followed by T, but many fewer in which K was followed by K. Do these numbers on the diagonal indicate that the OCP-Place constraint, as it were, is stronger in the case of P and K than it is in T? Well, these are just the raw frequencies of co-occurrence. O over E tells us we should do a couple of operations on this table before concluding whether the constraint has greater strength in one case than another. First, we'll just change all the counts to proportions by dividing by the total number of pairs. The O over E statistic is invariant to changes in the total data set size. So we can just get rid of that total size, just normalize it out. So now things look like this. And we have some numbers along the diagonal, this one being the biggest, these two being smaller, this one higher than that. So again, you might conclude at this point and say the OCP, or whatever phonotactic it is stronger here and here than it is in this case, but that we're not quite done applying the O over E yet. We have to divide each cell, for example this one, by the product of its column total and the row total, or the row sum. And we do that for each of these cells, divide each one by the corresponding product of the corresponding row and column sums. And we get this. Okay? So as we've seen looking at this data, we get bigger numbers in the T cell than in the other diagonal cells. And the way that the way that the observed over expected statistic has been used in studies of OCP-Place is to stop here and conclude that the constraint is stronger in these two cases than in this case, because the numbers, the O over E values, are lower. Okay, so that's exactly the method that has been followed in Pierre-Humbert's paper, in the Frisch et al. Paper, in the Kutzi and Pater paper, and so forth. So a user of ORE would conclude that the OCP, or whatever phonotactic we're looking at, is stronger for the KK case than for PP, and stronger for PP than for TT. And so the question is this correct? Is this a statistic that actually measures the strength of the phonotactic constraint against those combinations? And I'm going to say no. So we've got to think about why the O over E has the particular form that it does. So it's a ratio of a term that's proportional to the frequency of the combination. That's in the numerator. over the product of terms that are proportional to the frequencies of the two elements that we're combining. Okay, so this is just a repeat of the definition, and it's easier to think of the terms of the proportions here. So it's the proportion of cases with the combination divided by the product of the following, the proportion of the cases that begin with the first member of this combination, and the proportion of cases that have the second member of this combination as their second member. The only way one could rationalize this statistic, I think, is as follows. We assume that in the population, whatever's generating our Arabic or Muna data, whatever probabilistic process that is, in that population, the probability of a particular combination is a factor of really 3 terms plus a normalization constant. There's a term that says how good or bad it is to have this I in the first position, AI in the first position. A term that says how good or bad it is to have B, J in the second position, times a term that's related to how good or bad their combination is. We've been talking about how bad combinations are according to the OCP-Place. And we would ideally like to measure this term some way. If we knew what these two terms were, we could divide some estimate of this probability by these two terms, and we would get this factor up to some normalization constant that would be the same for all of our pairs. And so if we were looking at correlations or something, that normalization constant wouldn't screw us up, wouldn't have any influence. And we would be able to see these values in a really straightforward way. Okay, so if we assumed that the proportion of cases that show this combination is tending to this true probability as we get more data, which is certainly true, and we assumed that this value, the proportion of cases that have A sub I in the first position, was tending to this value, and this was tending to that value, then of course we could take these values and divide this one by their product and get something that's clearly related to what we're trying to measure, which is the strength of the constraint on their combination, factoring out how good or bad each of the two members of the combination are independently. But unfortunately, that's not what the ovary statistic does, and it's pretty easy to show. I constructed that table of numbers that we were looking at earlier in the following way. I said that, well, it's perfectly fine, it's perfectly good to have T in the first position. It's a little bit worse to have P and a little bit worse to have K. So these are the terms in the first part of this expression for the three abstract consonants that can occur in the first position. So this is best, worse, and then worst. And just for fun, I use the same weights up here for the second position. So T is good in all positions, P is a little bit worse than T, and K is a little bit worse than P in the second position, just like in the first, okay? So these are the effects for the rows and the columns, or for the margins. But we're interested in the effects that are inside the box. And so I said, look, all combinations are perfectly fine. That's what these ones indicate, except those along the diagonal. But those along the diagonal are getting exactly the same penalty. The OCP-Place, or whatever constraint it is that's restricting the combinations, has, by definition, the same strength in all three cases. So the true diagonal effects are all equal. If you go back to the over-E table that we had and pull out just the diagonal, you see that the diagonal values of the over-E statistic are absolutely not the same in this case. That's what we saw before. They're different values, quite different values, in fact. None of them identical to the true value. This one may be coming close. So over-E can make it look as if this type of combination, PP, is worse than this type of combination, TT, even when we know for a fact that that's not true, according to the parameters inside the box, which are the ones we're trying to measure. Those are the phonotactics against the combinations. So you might ask yourself, so what technically this means that over-E is not consistent, even if you were to give it an infinite set of roots it would not recover the right over E values in simple cases like this. It wouldn't recover the values along this diagonal. They wouldn't even be, the ratios of these values wouldn't even be the same. The ratios of all these values are 1. The ratios of these values are absolutely not 1. So they're not even identical up to some constant. So you might ask, why is this happening? And I'll just sketch it out briefly. So it's true that as your data set gets larger, the proportion of cases that show this combination is converging in probability to the true probability of that combination. That part's true. And I think the only way to rationalize over E is to think that it was crafted thinking of a definition like this. Okay? So that's true not just for this combination of AI and BJ, but for all of the combinations of the segments that can occur in the first position and the segments that can occur in the second position. And so you can use those, you can use the fact that all of these proportions are tending to their true probability values as the sample size goes to infinity to identify what would the over E values be in a table like the one we were looking at as the sample size goes to infinity. And it would look like this, just doing the math, which I won't go through, which can be simplified to a certain extent. This is the line I want you to focus on, okay? As the sample size goes to infinity, over E does not take necessarily the value that we want it to, the strength of the term that's the phonotactic against this combination. It takes the value which is that term multiplied by this hairy monster, which does not generally simplify to 1. So instead of measuring what we would like to measure, which is this, in general measuring this multiplied by some other number that we don't know. So we can't even, I don't think, outfit over E with some kind of corrective glasses that would take this number and divide it off, leaving us just these co-occurrence weights or co-occurrence terms. I don't think we can do that. It turns out that there's one situation in which over E is perfectly right. And it's the most boring situation possible. It's the situation in which all of those terms inside the box are exactly equal to 1. When there are no phonotactics on the combination of consonants, then over E will, yes indeed, always return the value 1 if the sample is big enough. It will tell you there's no association, there's no OCP-Place, there's no effect. So you can show that pretty easily that this term is identically equal to 1 if all of the lambda values in the entire table are equal to 1. If one of them is not equal to 1, then I think all bets are off. I don't have a set of necessary conditions for over E to measure those co-occurrence terms correctly. I just have sufficient. So that was our statistical interlude, and we're coming to the end now. So here's the deal. Over E is inconsistent as a measure of the strength of the OCP-Place. And it's inconsistent in a very particular way. It exaggerates, overvalues the strength of a phonotactic restriction like OCP-Place when you look at combinations of consonants that are already of low probability, independently of lower probability. So when you have lower probability margins, it looks like the constraint on the combination is stronger when in fact you can show in cases like I've designed that it isn't. And this isn't a problem just for over E. If you use the elements of the chi-squared statistic or the elements of the g-squared statistic, or you use transition probability to measure the strength of phonotactic restrictions, you run into exactly this type of problem. Exaggeration of the effects for combinations that would independently be of low probability. Okay, so here we are in the last section. So recall that we got into this dilemma with Muna. Muna has a weak-ish OCP-Place constraint on coronal. It's stronger for labial and dorsal. In that respect, it's like Arabic. But Muna doesn't have the type of inventory that Arabic does with so many coronals. Therefore, we couldn't straightforwardly use the natural classes similarity metric to solve that problem. But how did we know that the OCP-Place constraint was stronger for the labials and dorsals in Muna than it was for the coronals? We only knew through the over E statistic values. We know the over-E statistic values are not pure measures of the strength of the OCP-Place or other phonotactics on restriction, on combination. So Muna needs to be revisited, and Marike and I have been revisiting it, and as usual we've fit a million different models, so I'm just going to give you a little sample here. We saw that the OCP-Place strength can be exaggerated by over-E when the consonants that are combining are of relatively low probability. So we might ask ourselves, are labials and dorsals overall of lower probability than coronals in Muna? And it turns out to be that that's true. So if you look at the first member of a consonant sequence, you get more coronals than labials and many more coronals, more than twice as many as you do dorsals. So we know that under this type of situation, it's likely that over-E is going to tell us that the OCP-Place constraint is stronger here than it is here, because the marginals are different. And same thing for second position of a consonant in a sequence. So there is a sense in which Muna and Arabic are the same. It's not in their inventories, but it's something about the distribution of different places of articulation in the roots. There are many more coronals in the roots than there are labials or dorsals. In Arabic, that's largely explained by the fact that there are so many more coronal types of segments. In Muna, it's explained by the fact that there are relatively few coronal types of segments, but each one has a pretty high frequency in the words of the language. Okay, so why did people use over-E and transition probability and elements of chi-square and so forth? Why did they use them in the first place? They used them presumably because there was a perceived difficulty in combining constraints on single segments, like, for example, don't have g in the first position of a root, or don't have ma in the second position of a root. A perceived difficulty in combining together those types of constraints with constraints on combinations, like don't have ka and ga in adjacent positions, or somehow estimating the weights of those constraints or whatever. Well, luckily we have the log linear or max entropy math to solve this problem. So this type of formalism will allow multiple overlapping and cross-cutting constraints, and we can estimate their weights, and everything's convex and nice, since we're not dealing with any hidden structure here. So Marike and I have a very simple log linear model for Muna. Works the same way for Arabic. I want to show you that. So there's one constraint on consonant sequences, and as our old friend OCP-Place. It says given two consonants that are homoorganic and that are not separated by any other consonant, maybe separated by vowels, assign a violation that's proportional to their similarity. Similarity is measured in that high-dimensional natural class space, just as Frisch proposed. And we have a simple model for the individual consonants. So there's one constraint for every consonant that could occur in the first position, so there's a particular weight for that. And there's one constraint for every consonant that could occur in the second position. It turns out that even if you don't allow those weights to be estimated along with this one, maybe you estimate them separately in a way that's oddly similar to what's happening when you calculate over-E values. Even when you estimate these independently, or just take them from the calculations of over-E values that people have used in the literature, if you combine their weights with the weight that you learn for the OCP-Place constraint, you get a very nice description of the data that captures a lot of the subtleties. So here's how you do it. You define the harmony as the negative of the weighted constraint violation. So we have some weight for the OCP-Place constraint. That's language specific. But the similarity values are not. They're calculated in the, well, they're not calculated in a way that's language specific. They're calculated based on the inventory of the language and the natural classes that that inventory gives rise to. You add to the weight of this, the weight or the penalty for having alpha in the first position and beta in the second position. If you just add all these values up, all these harmony values up, once you exponentiate them, you just add them up over all the consonants that can occur in the first and second position, you get some normalizing constant. You can divide each of the exponentiated harmonies by that constant z to give you a probability of that co-occurrence. It's a nice finite set. There are no difficulties in dealing with this set. We just use maximum likelihood weight estimation, but we easily could use some other method, more Bayesian method, for example. And we've looked at linear regressions between the probabilities as predicted by the model and just the frequencies of the consonant combinations. Not these funny over E values, but just the raw frequencies. We're taking care of what over E was intended but did not take care of with these penalties on the individual consonants. We're starting to use a more sound model of regression, the Poisson regression. Since the counts of a consonant sequence can't go below 0, it's not really appropriate to use linear regression. So we took the almost 8,000 tokens of 625 consonant pair types from a Muna corpus, and we're getting very good R-square values when we compare the probabilities that we're predicting from the model with the frequency counts. And you have to remember that we have an extremely simple and in some respects just stupid model of the phonotactics. We're saying there's no restriction on the combination of consonants except the OCP-Place. And that's known to be false in the language. But we just wanted to see how well this very simple model would do. And it seems to be doing very well. So I'll just show you the picture before we wrap up. So we're missing some cases like RR is much worse than we're predicting it to be. And for some reason, sa followed by la is much better than we're predicting it to be. But for the most part, we're able to account for the Muna pattern. The Arabic pattern doesn't look as clean when you plot it this way, but it doesn't look like that clean for any model of phonotactics. So there's something further to be learned about the Arabics. We've probably squeezed all we can out of the OCP-Place. So let me just conclude. Apparent variation in the form of a constraint like the OCP-Place, it doesn't have to be true variation. There may be other factors that are interacting, like the size of the inventory, the number of coronals, for example, or the probability of the consonants independent of their co-occurrence. There may be a misdescription in certain sense of the variation. So the statistical method that's being used, even though it may have been used for 15 years or so, may be incorrect. And you may not have the right model of constraint interaction. So one has to examine points like this before concluding that there is true variation as opposed to universality. So here's what we have so far. For the languages that we've looked at, which are Arabic and Muna, and I'm starting to look at Javanese and English, for the patterns that we know well, this gradient version of the OCP-Place, which makes reference to natural class similarity, is accounting for the data quite well when put into the log linear framework. And so we might seriously consider that it is a universal. And of course, I'm not concluding that it is, but it's at least a candidate for universal. Some of the things we're doing now, well, I've assumed that native speakers like their statistics to be consistent, and they might just prefer the use of over E, and I've assumed that they use these constraint-based models and so forth. All of these points raise issues of psychological reality. Am I talking about just the numbers, or am I talking about the speakers and their grappling with the numbers? So we're currently replicating all of this with English. It's just easier to find those speakers than Muna speakers. There's a lot of work we have to do to reanalyze the literature, since so much of it is used over E in similar statistics. And that one question that always bugs me, and I don't have any answer for it, is it would seem to be the case that variants of the OCP of the type that McCarthy proposed and others have proposed are very simple. I mean, I have a model that can learn them. And so in some sense, there's a conundrum. If they're so simple, if it would be pretty trivial to learn them, why don't they exist? Why would these phonotactic systems obey universal laws like the universal form of the OCP-Place that I'm proposing? I don't have any explanation for that. So I think that's it. Thank you very much. Yes.
I most likely misunderstood, but I have a question regarding the table you showed for the ovary.
Yes.
Yes, with the next. Yes.
Yes.
Am I supposed to interpret this as a table of proportional values? Like, what is this table supposed to be?
I see. Yeah, I didn't explain it very clearly. So The idea is that you get the probability of a combination, for example, T followed by P. You get the probability of that by multiplying this value, which is the row contribution, that top value, which is the column contribution, and this one. And then you normalize. You sum over all the probabilities in the table. So that's what it's supposed to mean. It's supposed to connect, but I didn't do it very well. It's supposed to connect to this equation down here. So there's a row term, column term, and then a combination term. And the table shows the row column terms over here, columns, and then the combination term, the co-occurrence term in the middle. I should have expanded it out into the probabilities.
So it's three potential functions. That's the left thing, the right thing, and the binary potential function.
I think it'd probably be fine if we just labeled, because the way it is right now, it kind of looks like what's in the box is, product.
Yes, it does look like that.
We just label one of them to say,
thanks. Okay, I'll definitely do that.
And that seems like a
Yep, I got lazy. Yes?
Is there any way you can link kind of the probabilities of these things co-occurring somehow with the physical dynamics of actually how they're produced? Is there anyone who can say, these are easier to say in some physical model of articulation?
I'm very puzzled about, not your question, but I'm very puzzled about the facts. Because when children are learning to speak, not just English, but French, many other languages, they often produce exactly this type of sequence in which there are two consonants. They may be identical or not identical, but they share place. So English learning kids often say guck for duck. And guck is one of those cases in which you created something homoorganic from something that wasn't. And so you've gone in the exact opposite direction of this constraint. And so I have often pondered what could be the articulatory basis for this constraint. And for many other constraints, the articulatory basis is clear. For this one, I don't know. It's also the case that when you have people do reiterant speech, have them just speak as fast as they can, saying some nonsense syllables, they're very fast when the consonants are repeated or when the features are repeated.
So maybe it's more cognitive.
I don't like to back off to say that it's arbitrary or cognitive in some way, but yeah, I don't understand its basis yet.
So it's actually a functional constraint in adult language to signal that the speaker is not a child.
Yeah, yes, exactly. This constraint got reinforced by the older child not wanting to sound like the younger child and undoing some cases of putative harmony.
Child wanted to be left to talk too fast.
That's right. Yeah, exactly right. That. Let's take time and savor our words with their different places. Yeah. I don't know what it is.
Well, it could also be a perceptual limitation rather than a production limitation. So rather than saying, our vocal tract is such and such, therefore OCP-Place makes it easier. Instead say, well, our ear canal is such and such. So having this allows listeners to pick up on differences rather than, especially in noisy app.
I see. That's interesting. So maybe there's some kind of repetition blindness effect, that it's difficult to hear the same gesture or whatever within a short period of time. It is true.
Yeah, you can make this crazy argument that it has to do with the representation of phonology in the brain and some distributed pattern of firings. And that you can't, you lose the association of, if you have a word like duck, then the listener might think it's actually cog or something. And they end up losing the association of position with the features.
I see. Yeah, that's an interesting idea, and I think that's similar to an idea that Luigi has been pursuing. That's
Adam Wayman, who's doing a dissertation with Colin and me, is utilizing the notion that representations are attractors. And so for this reason, when things are similar, they're attracted to one another. And this is creates some disharmony in the representation, which he argues can be improved by making things more dissimilar. So the puzzle is that there are two diametrically opposite sets of pairs, and the OCP is one aspect of that. So that there are assimilations as well as dissimilation. So the OCP is the similar side of the coin, and that is a puzzle as to if it's good to be similar, what should also be good to be dissimilar. But if you entertain the notion that representations are a attractor, I think that does solve the puzzle, because then there's two ways to remedy the attraction. One is to be farther away, so to diminish it. The other one is to comply with it and become more similar or identical.
So are you, when you talk about representations as attractors, I don't know if you mean
Segments.
synchronously, synchronically or diachronically?
Synchronic.
Because you could also imagine some diachronic effect, whereas GUG gets normalized either away from GUG or toward GUG, so that words that are too similar end up disappearing.
Oh, synchronic. Synchronic grammar. That's how the brain works. That's how we represent a structure. And you just go for the maximization of harmony, as you know, T. And sometimes that works by making things more dissimilar, sometimes more similar.
So in languages that do allow violations of OCP-Place, do you see those forms changing over time?
I don't think that's known. And Arabic would be the place where you would want to look, because it's such a long historical record. But the thing is that the consonants are changing in many other ways, and so I think people have found it difficult to track the OCP-Place's effect on the historical pattern. Yeah.
The Frisch paper, the Frisch et al. paper,
Yeah.
had some perceptual story, and basically they gave a diachronic type of story based on perception.
There just wasn't any evidence for it, so I
Right.
think, yeah, it's kind of it's up in the air as far as they're concerned.
So you have time for one or two more questions?
Okay, Kyle.
Or you'll plan?
So I was wondering if you could say why, or if you have any ideas on why this natural class similarity metric is the metric that's used. I mean, it's not the most intuitive, as you said
Yes.
yourself, and there's something very non-local about the computation that you have to do calculating
Yeah.
that kind of similarity.
Yeah. Stefan does have some talk in his dissertation about if you represent, he had a kind of connectionist representation of the featural components of the segments, and there was some kind of feedback or something that happened amongst the different representations of the segments that he claimed gave you the same similarities that you get from the natural class similarity metric. But honestly, I never fully understood how that was supposed to work.
Story to tell about it, actually.
Oh, okay, well, I'd like to hear that then, yeah.
I mean, I can say it now, or I can say it
Oh,
after.
no, say it now, yeah.
Okay. If you and somebody else both went to a small college, or you both lived in the same house or something like that, we think you're probably pretty similar. But if you both went to the University of Maryland, which is huge, then that doesn't make you particularly similar, because everybody goes to the University of Maryland, and then we need to know what crowd you ran with when you were there. Or if you want a different analogy, it's to people who have 2,000 different words for snow. The distinctions between they've got all these subcategories, so the distinctions between different kinds of snow become more salient. It's sort of how much substructure you have. I mean, I could also make an analogy to WordNet. Some parts are highly refined.
Doesn't it, that definition of similarity, doesn't it covertly endorse some kind of dispersion theory in that it will tell you that, the distances or similarities are what you can observe from the inventory. So then indirectly it tells you that the inventory is a set of equidistant members. So if you want the distance, the inventory is very rich, but the distances are. So if distances are large, then
Well, see, it adapts to the size. It adapts to the size and doesn't make all the members equidistant at any size. I mean, in general. So.
Well, if there weren't any natural classes that, if there
Yeah,
weren't any
yes.
classes in the University of Maryland.
Sure.
So if Carnell were just one class, we didn't have some
Absolutely.
So that's the coronos is the University of Maryland.
Yes, exactly.
Yeah, exactly.
Right, and the crowds are the natural classes within the University of Maryland. I didn't make any analogy for that.
So basically it tells you the reason you have more kernels is because there's more space within that set. there's more space and more members. in that
Yeah,
sense.
you could go the opposite direction. They were thinking of it because there are more Cornells, it's University of Maryland.
Yeah.
Not because it's University of Maryland, many people can go there. Yeah.
But you could go the other way.
Yeah, you go the other way.
But to the extent that I may be right in suggesting this, that, there's a covert endorsement of dispersion theory. The case of the contrast between Arabic and what was the other language?
Muna?
What was it?
Muna?
Muna.
Yeah.
Muna. That puts the kink into it, right? Because then dispersion distances are not reducible to phonetics.
Oh, well, I'm arguing that you get the right distances in Muna from the natural classes similarity metric. Right? I'm not arguing that you have to change those distances to make them more like Arabic.
No, but what I'm saying is
Exactly right.
that the two different inventories, these are languages that have different inventories. And there's something special about Cornells in that they have more space. And the fact that the two languages differ, is not explained. I mean, you're not able to reduce distances to phonetics, because the phonetics of individual segments are presumably the same in the two languages. And so, but you argue that frequency is involved there.
Yeah. Yeah.
And so one could perhaps reconceive dispersion theory as the inventory also, in addition to phonetic distances, you also have to consider frequency. So if something is, high frequency, then it has to occupy more space.
It's conceivable.
Something
Yeah,
like
it's
that.
conceivable. Yeah, that's possible.
So if
Yes.
there is a correlation between inventory size and frequency along the lines of what you suggest, then that would have to be captured.
It's hard to see that as not just a necessity. So if you have a lexicon of about the same size, if there are more consonants, some of them are going to have to be less frequent. Okay. Yeah.
So I think maybe we should wrap up, and you can
Okay.
deal with the rest of us who have questions.
Okay. Thank you.
Face to face.
Okay.
Let's
Thanks.
thank our speaker again.